Hello, this is the section 5.6a lesson. The topics in this lesson come from the first half of section 5.6. And the topics in this section are going to be very similar to what we did in section 5.4 in that we are going to be comparing two independent populations. The biggest difference here is that instead of comparing population proportions, we're going to be comparing population means. So to illustrate this idea, let's look at example 561, where a researcher wants to compare two different diets. And we're going to generically call them diet A and diet B. And let's suppose that on diet A, they take 10 volunteers and put them on the diet for a few months. And then after those months are over, they record the weight loss of each person. And they calculated a mean weight loss of 4.5 pounds. And they also calculated a standard deviation of those 10 weight losses to be 6.5. And then on diet B, they put a different set of 10 people on that diet for a few months. After those months, they record their weight losses. Their mean weight loss was 3.2 with a standard deviation of 4.5 pounds. Okay, so notice that we've got here two independent groups of people. These 10 people up here are not the same as these 10 people down here. What happens to these 10 people has no direct effect on these 10 people here. So we have two independent groups of people. Okay. If we compare these mean weight losses, it looks like diet A maybe does a little bit better than diet B. So let's use this information to test the claim that the mean weight loss of everyone on diet A is higher than that on diet B. Now again, notice as in the first example, we are comparing means from two independent populations. Our independent population, our first one is all people on diet A, not just these 10 people. We're interested in all people on diet A. And then second population is all people on diet B. We want to compare the mean weight loss from this first population to the mean weight loss from this second population. Our data indicates that maybe this first mean is bigger than the second mean, and so that's what we're going to test. So again, we have two populations, and notice this word independent comes up again. Independent means that what happens to the first population has no effect on the other population. It's reasonable to assume that what happens to these people on diet A has no effect to these people on diet B. Notice that they're 10 different people. It's not the same people doing the diets twice. It's 10 people doing A, another 10 people doing B, so they're independent. And so again, that word independent is very important. Now, before we get into the details of this test, this hypothesis test, let's start setting things up. We're going to go through the same 5 steps as what we've done before. Number 1, define the parameters. Well, and again, we've got two populations, so we're going to have two parameters. I'm calling mu1 and mu2. Mu1 is the mean weight loss of all people on diet A. Mu2, the mean weight loss of all people on diet B. Again, we stress these words all here because we're making a claim about larger populations of people. We're not interested in just the 10 people on A and just the 10 people on B. We're interested in larger populations of all people taking these diets. Now our claim in mathematical notation is that mu1 is bigger than mu2. And so our hypotheses are going to be, the null is going to be that mu1 equals mu2. This is a statement of the status quo. We might expect these diets to be equal if we didn't have any data indicate otherwise. Our alternative is going to be that mu1 is greater than mu2. This is what our data seem to indicate is true, so that's going to be our alternative hypothesis. Now, we're going to note that we could rewrite these hypotheses in a slightly different way. If we take our null hypothesis, for instance, and take the mu2 to the left, we could write it as mu1 minus mu2 equals 0. And likewise, we could do the same here with the alternative and get that mu1 minus mu2 is greater than 0. Basically, as we're going to see when we talk about the formulas, we're going to use kind of this form of the hypotheses. But when we do things on the calculator, we're going to use this form of the hypotheses. Both these forms are completely equivalent. They're just different ways of saying the same thing. Now let's talk about the second step of calculating the test statistic. Back in section 5.3, and we talked about testing a claim about a single population mean, we had two different types of tests. We had a z-test and a t-test. And likewise, when we're comparing two population means, we're going to have a z-test and a t-test. The biggest difference between these is that in a z-test, the test statistic is a z-score, so it has a standard normal distribution. In a t-test, the test statistic is a t-score, and so it has a student t-distribution. Both these tests are called two-sample tests because our data come from two independent populations. Now we're going to use the two-sample z-test in a couple of different situations. Number one, if our population variances are known, or if we have large sample sizes. Now this first case where our population variances are known, that almost never occurs, so we're rarely going to see that. If we have very large sample sizes, then we can use the two-sample z-test. Now one complicating factor here is that with our two-sample t-test, we have a couple of different versions of it. First version is where we assume that the population variances are equal. The second is where we do not assume them to be equal. Now, kind of the default rule that we're going to use here is that we're always going to use the t-test, and we're not going to assume equal variances unless the problem indicates otherwise. Okay? So again, just like in section 5.3, we always used the t-test. And now in this case, we're not going to assume equal variances unless the problem states differently. Okay, so let's talk about how we calculate the test statistic in these t-tests. So our two-sample t-test, the purpose is to test a claim regarding the means of two independent populations where the null hypothesis is of the form mu1 minus mu2 equals c, where mu1 and mu2 are two population means, and c is some number. Now in this particular example, c is equal to 0, and that's probably going to be the most common value of c, but c could be really any number. So the first step is that we select independent and random samples from each population, and then we calculate the mean and standard deviation of each sample. And that's exactly what we've done here in this example. We selected 10 people from that first population, 10 people from the second. We recorded their weight loss, calculated the mean weight loss, the standard deviation of the weight loss. That's what we've got. Okay. Now let's talk briefly about the formulas here for the test statistics. These formulas are rather complicated, but luckily we rarely have to do them by hand. We're going to let the calculator do the work most of the time. So if we assume equal population variances, which is usually not the case, but if we do that, then we calculate the test statistic using this formula here, where x1 bar and x2 bar are our sample means, and c is that number that appears in the null hypothesis. In the denominator, we have our two sample means, and then we have this quantity sp, which is calculated according to this formula right here. S1 is the first sample standard deviation, S2 is our second sample standard deviation, and S sub p is called the pooled standard deviation. Now remember that word pooled because we're going to see that again when we get to the calculators. Okay. Now the critical value for this type of test is a t-score with n1 plus n2 minus 2 degrees of freedom. And that critical value comes from table C3 in our appendix. And a p-value is the area underneath a student t-density curve with this number of degrees of freedom. So again, it's an area underneath a student t-density curve. Now if we assume unequal population variances, our test statistic is calculated according to this formula. Looks very similar to the previous formula, a bit different. We see that number c here. But notice that instead of that pooled standard deviation, we have S1 and S2 appeared. And our critical value is a t-score with this many degrees of freedom. This is a rather complicated formula for calculating the number of degrees of freedom. But luckily we're not going to have to use that formula because it's built into the calculator. Now, requirements for this formula, for this hypothesis test, are number one, both samples are random. That's always a requirement. We've got to have random samples. Number two, they're independent. Again, independent means that what happens to one sample or one population has no effect on the other. And then number three, both populations are normally distributed, or both sample sizes are greater than 30. Now in this case we have samples of only size 10, so we're just going to, for the sake of argument, assume that everything's normally distributed. So let's go back to our example here. We're comparing these two diets. Here's the sample statistics from the first diet, sample statistics from the second diet. And for the purpose of this example, we are going to assume equal population variances. And again, that's typically not the case, but that's what we're going to do in this case. And we're also going to use a 0.05 significance level. That's our default significance level. Okay. So first step was to define our parameters and state our hypotheses. Well, we've already done that. Here's our hypotheses. Notice that the number C here in our hypotheses is 0. And so the next step is to calculate our test statistic. We're assuming equal population variances. And so we calculate our pooled standard deviation there. We get 5.59. And then we calculate our test statistic. There's where our pooled standard deviation comes in. And we do that arithmetic. Comes out to be 0.52. Okay. Third step is to calculate our p-value, or equivalently find the critical value and the critical region. So our critical value is a t-score with n1 plus n2 minus 2, which is 18 in this case, degrees of freedom. And if we look that up from our z-score table, we get 1.734. P-value is the area underneath a student t-density curve with 18 degrees of freedom to the right of our test statistic. It's to the right because the alternative hypothesis is that mu1 is greater than mu2. Now, like all the other t-tests before, we can't find that using tables. But if we use the software, the p-value comes out to be 0.305. Okay. Next step is to come to our technical conclusion. So our critical region is this. Notice that the test statistic is not in that critical region. Also note that our p-value is much greater than our significance level of 0.05. And so in either approach, we would not reject the null hypothesis. Last step is to state the final conclusion. The original claim did not contain equality, and so we would state that the data do not support the claim. So the claim was kind of that that diet A was better than diet B, but our hypothesis test does not support that claim. So in even less technical terms, we would conclude that there does not appear to be a statistically significant difference between the diets. Our sample means appear to be quite a bit different, but our hypothesis test tells us that that difference isn't big enough for us to conclude that there is a difference between these two populations. Now lastly, let's talk about how to do this two-sample t-test on the calculator. If we go to the Stat Test menu and choose option 4, the two-sample t-test, notice that option 3 is the two-sample z-test, which we're rarely going to use. So if you press enter, you're going to get a window that looks like this right here. Like with our other t-tests, we have two options how we input our information. If we have raw data, then we can enter those two samples of data into the calculator and then choose the names of those lists, and it'll calculate everything for us. But that's not what we have. We don't have raw data. Instead, we have summary statistics. So we're going to choose this second option, stats, and then we're going to enter our first sample mean, standard deviation, sample size, second mean, second standard deviation, second sample size, and then notice the down arrow there means there's more to input. So if we scroll down, we see that the next thing that we need to input is the form of our alternative hypothesis. Now, one note about the calculator is that the formula that's built in only works for null hypotheses of the form mu1 minus mu2 equals 0. So this number on the right hand side has to be 0 in order to use these built-in formulas. And that's what we have here. In this case, that number C was 0, so this isn't a big deal. So remember, the first form of our alternative hypothesis was that mu1 is greater than mu2, and so that's what we're going to choose right here. Next, we need to choose either pooled, no, or yes. And we determine which option to choose there based off of that assumption of whether the population variances are assumed to be equal or not. We choose yes if the variances are assumed to be equal, and no if they are not assumed to be equal. Now in this case, we are assuming that the population variances are equal, so we're going to select pooled yes. And then select calculate and press enter, and we should get a window that looks like this up here. So the first row tells us that we did the 2-sample t-test. Next is the first form of the alternative hypothesis, which is correct. Here's our test statistic, identical to what we got by hand. Here's the p-value. That's the most important number. And then right here is the degrees of freedom, which is just n1 plus n2 minus 2. Next, it outputs all the information that we entered, x1, x2, our sample standard deviations here, our sample sizes down here. And then right here is that pooled standard deviation of 5.59. So that's all there is to doing the 2-sample t-test on the calculator. Again, the most important value here is the p-value. Once we have that p-value, we can come to our technical conclusion and go from there. Now, lastly, just for fun, let's redo this example, but let's do not assume equal variances and just see if there's any differences between what we just calculated. So we're going to go back to the same test, again, the 2-sample t-test. We're going to enter everything in this exact same, except we're going to choose pooled no. And that's the only difference. So select calculate and press enter. And we're going to get a window that looks like this. It looks very similar to what we just saw. There's our alternative hypothesis. There's our test statistic. There's our p-value, 0.305. Now notice that's a little bit different than the p-value that we got when we assumed equal variances, but not that much different. And this p-value is not going to cause us to change our technical conclusion or our final conclusion. And then next is that degrees of freedom that was calculated using that very complicated formula. So we see that here we've got 16 degrees of freedom. And then here's the sample statistics that we entered. Notice that it does not give us a pooled standard deviation, because the pooled standard deviation only is calculated when we assume equal variances. So again, this p-value here is the most important result. We would use that to come to our technical conclusion and then our final conclusion. In this case, there isn't a whole lot of difference between assuming equal variances and not assuming equal variances. Some cases there may be some more difference.